Hello, my name is Kristina Miller, and today I will be talking to you about fast and guaranteed safe controller synthesis for nonlinear vehicle models. And so this is work that I have done with Chuchu from Caltech and my advisor Sayan Mitra. So before we dive into things, we should define exactly what we mean by a controller synthesis problem. So with the controller synthesis problem, we're going to have some system model. In this case, we're dealing with a nonlinear dynamical system, and the discrete time dynamics of the system are written out here. So f is just going to be some nonlinear function, x of t is going to be the position of the system at time t, and then u of t is the control input at time t. And so the specific type of nonlinear systems that we're dealing with are vehicle models. Additionally, we will be using the continuous time dynamics of this system, as this is a common practice in robotics. So the specifications that we're going to be finding controllers for are reach of voice specifications. Here's an example of a reach of voice specification, and we found this scenario from the Scott's paper written by Runger in 2016. And so as part of this reach of voice specification, there are three main components to note. The first is the starting set, labeled here as S, and that's just the blue set shown on screen. Next is the goal set, labeled as G, which is the green set shown on screen. And then finally, we have the unsafe set, O, which is shown here by the red obstacles. And so the goal of this controller synthesis problem is to find a controller or control input such that for any system that starts within the starting set, we want to reach the goal set while also avoiding all of the obstacles in the unsafe set. And here's just an example of what that might look like. Here's a real-world example of where we could use this controller synthesis problem. This video is from Waymo. And basically the goal is for the car to reach the top left lane while also avoiding all of the obstacles that it perceives around it. It's important to note that perception and sensing is an important problem in autonomous systems, but we're going to be focusing on the controller synthesis aspect once we know where all of these obstacles lie. Additionally, this scenario shown here is a dynamic scenario, but we're focusing on static scenarios where the obstacles won't move. But we're working on extending this problem to also synthesize controllers for scenarios where the environment is dynamic. So there are various related solutions to this reach of voice specification problem, and so we'll just touch on a few here. The first is model predictive control, and so in model predictive control, we are trying to find the optimal control input for a system that will drive our system from the start set to the goal set. Another method is using discrete abstractions, where we will discretize the state space and then find a discrete controller that will satisfy our reach of voice specifications. There's also safe motion planning, where we can compute the error bounds for the reference trajectory beforehand and then find our reference trajectory that our system should follow. Finally, we have sampling-based planning methods, where we will sample the state space and then try to find a valid trajectory that will drive our system from the initial set to the goal set. And so for each of these various solutions, there are a lot of papers that are associated with them, such as for MPC, there's both implicit MPC, explicit MPC, and the optimization problem can be formulated as LP, QP, or MILP problems. Additionally, MPC can help find controllers for nonlinear systems. In discrete abstractions, there's also several tools that are out there, such as Cosima, Pessoa, LTL-MOP, Tulip, and Scott's. In safe motion planning, we have FastTrack, RTD, LQR trees, and funnel libraries. Finally, in sampling-based planning, we have probabilistic roadmaps, rapidly exploring random trees, and fast marching tree. And with these sampling-based planners, there are also several libraries that have these planners that we can use, such as MoveIt and OMPL. And one thing to note is that with sampling-based planning, we can get statistical guarantees, but what we're trying to solve for will give us deterministic guarantees. So in this work, we're going to show how we can combine stat solvers and control theory to perform effective safe controller synthesis for continuous nonlinear systems, and this controller will come along with soundness guarantees. So how can we formulate this controller synthesis problem using stat formulation? Remember that we have a system model that follows some nonlinear dynamics, and we also have to solve for a reach-avoid specification. So one way that we can formulate this as a stat problem is to say we want to find some control input such that for all time, the real trajectory of the system does not intersect with the unsafe set, and that trajectory will start in the initial set and end in the goal set. So can an SMT solver handle this formulation effectively? Unfortunately not, as the nonlinear constraints over the reals makes this problem hard. In a previous work in CAP 2018, we showed an effective way to reformulate the problem for linear systems as a stat problem over quantifier-free linear real arithmetic. Unfortunately, we are now dealing with nonlinear systems, so we can't use this method anymore. Additionally, there exists for all formulas do not scale well to large numbers of variables using SMT solvers, as quantifier elimination in real algebra has double exponential complexity. So the key contribution of this work is that we want to show that we can synthesize controllers for nonlinear systems by using a reference path synthesis along with a tracking controller from control theory. For this reference path synthesis, we note that nonlinear vehicle models can follow linear paths. So we're going to be using piecewise linear reference paths, as we see that these paths can be synthesized using stat problems over quantifier-free linear real arithmetic. And we can also pre-compute the tracking error for the entire reference path. Next, we will look into the tracking controller. So nonlinear vehicle models cannot follow these reference paths exactly due to inertia and actuation limits, and also various other uncertainties. So using control theory, we can find the bounds on the tracking error between the actual trajectory and the reference trajectory. Putting it all together, we can use our reference path synthesis along with the help we get from the tracking controllers to find a controller that is valid for our reach-avoid specification. So now we'll dive into the reference path synthesis. So as previously stated, we're going to be using piecewise linear reference trajectories, and so we're doing this because we can find the error bound for each segment of this piecewise linear reference trajectory using methods from control theory. Note that these error bounds come from the tracking error and not just the size of our vehicle. So each piece of this piecewise linear reference path will have an error bound, and then we can concatenate these error bounds to get the bloated set, which will contain the real trajectory of the system at any time. Additionally, we'll say that Li is the radius of the ith bloated set, so L1 is valid for the first segment, L2 is valid for the second segment, L3 is valid for the third segment, all the way through Lk, which is valid for our kth line segment. So the way that we're going to find these piecewise linear reference paths is by finding the waypoints that define these piecewise linear reference paths. So we're going to define the obstacles in our unsafe set as polytopes, as this will help us with our stat formulation. We want to find the line segment between pi-1 and pi that is at least Li away from our obstacle. And we note that if both pi-1 and pi are outside of our obstacle, and the distance of pi-1 and pi are both at least Li away from the obstacle, then we know that this line segment is at least Li away from our obstacle. So the sufficient condition for the line segment to be at least Li away from O is shown here. So we want to check each surface of our obstacle. If for at least one surface, pi-1 and pi are at least Li away from that surface, then we know that that line is also at least Li away from the obstacle. And here, h, b, and the norm of h are all constants, so this formulation is linear. So taking that formulation, we can extend it to find our entire reference path. So we want to synthesize all of our waypoints through a stat problem over quantifier-free linear real arithmetic. So we want to find p0 through pk. such that P0 is equal to the start of our reference path, and so we just set this to be equal to the center of the initial set. Additionally, we want to check that each line segment is at least Li away from every obstacle in the unsafe set, and so this J right here is the number of surfaces inside of our obstacle. And then this O is the obstacle in our unsafe set. And then I is the number of line segments in our reference path. Finally, we want to check that our path ends within the goal set, which is shrunken by LK, again because the actual trajectories are at most LK away from the reference trajectory, or the reference path. So we know that if we shrink the goal by that LK, then we can guarantee that our system will end within the goal set. One thing to note is that the number of linear constraints grows linearly as the number of surfaces of the obstacles and the goal set increases. Now we will go over how we can find the tracking error for each one of these line segments. So if our reference path is shown here in the dotted line, the actual trajectory that follows that path is shown with the solid line. As we switch the segment that we're following, we see that the error will actually increase because the waypoint has changed. And so what we want to do is design a tracking controller such that the actual trajectory is contained within Li of our reference trajectory. The system will have some tracking error associated with it with the tracking error dynamics. And so the tracking error is just dependent on the actual position versus the reference position. So how can we find the bounds on this tracking error? We can use Lyapunov functions from control theory to find the bounds on the error dynamics. And so the key challenge is to compute tracking errors even when our waypoints change. So what we want to do is we want to use these Lyapunov functions to easily compute the bounds Li. So the tracking error can be bounded by our Lyapunov function and the Lyapunov function sublevel sets. And for each sublevel set, we can find the size of that sublevel set by looking at the previous sublevel set. We can find the size of the sublevel set for each line segment by only knowing the size of the sublevel set for the initial error. So because of this, bringing it back to how we can find the bounds on the error, we know that the trajectories are contained within Li of the reference path, where Li can be computed using the size of our Lyapunov sublevel sets. So finally, we can put it all together. We showed how we can find the reference paths using stat formulation. We showed how we can find the error bounds Li using methods from control theory, and putting it all together lets us synthesize controllers that satisfy our reach-avoid specification. In our paper, we show that we can iteratively partition the initial set and that each reference controller found for this, for each subset of the initial set is sound. We did all of this in an implementation that we call Factus. So this is a Python implementation, and we use the YCs library for finding the reference path. And the website and GitHub are shown here on screen, so if you're interested, you can go ahead and take a look at that. So our Factus implementation can effectively synthesize controllers for various scenarios. Here we show the 3D scenarios, so not only can we solve for scenarios in 2D, but we can also solve for scenarios in 3D. It's important to note that this is just the workspace and not the actual state space, as a 2D scenario, such as a car, has a 3-dimensional state space. Additionally, we show that we can synthesize controllers quickly for complex scenarios. And we also show that we can quickly partition the initial set to find valid controllers for each part of that very large initial set. So here's a table that shows how this implementation worked. So as you can see, each one of these scenarios, so the car and the robot scenarios are all in 2D, which is different from the state space. The car has a 3-dimensional state space and the robot has a 4D state space. And then we also show that in these 3D scenarios, we can have state spaces that are much larger, that are larger than our workspace, such as a 4D, scenario, and also some that could have 6 dimensions in the state space. We also show that all these controllers were synthesized in less than a second, and even as the state space increased, the amount of time that it took to synthesize these controllers did not increase that much. We also compared our factus implementation to RRT. So rapidly exploring random trees is a popular algorithm designed to effectively search non-convex high-dimensional state spaces by randomly building a space-filling tree. And so the average number of iterations it took to find a path for RRT was typically much higher than what our reference path synthesis would take to find a path. Additionally, the amount of time that it took to find a path for RRT was also much higher than the amount of time that it took for us to synthesize a valid trajectory from the initial set to the goal set. And so one thing to note is that in the Scott scenario, the scenario that we've been showing this entire time, RRT would typically time out, whereas we were able to find a valid solution in less than a second. So in summary, we show that we can have an open loop controller and a tracking controller to serve the purposes of reach avoid scenarios for a dynamical system. We also show that we can efficiently synthesize controllers by using stat problems over quantifier-free linear real arithmetic. And we also showed that the number of constraints in the stat problem is proportional to the number of surfaces of the obstacles and the goal. The experiments also show scalability, as we can find controllers within seconds. Some ongoing works, as previously stated, we would like to synthesize controllers for dynamic environments using this method, and we would also like to look into multi-agent planning, since we can quickly synthesize controllers for each agent in such a scenario. That's all that I have for the talk. Thank you very much for listening.